Today's objective is to prove if initial and final velocity is the same during angled launches. From my hypothesis, my claim is that my initial and final velocity will be the same throughout the time my projectile is in the air. From my evidence, I can use SOHCAHTOA to calculate the initial velocity, from where I can use the given angle from measuring using a protractor and the calculated horizontal and vertical velocities to find the hypotenuse, which could be my initial velocity. In addition, I can use the first kinematic equation to calculate my final velocity, since I would have already have the acceleration from gravity, time from recording the video, and initial velocity from the information above. My reasoning would be if both of my calculations were coming out to be the same, from using SOHCAHTOA to find the initial velocity and the first kinematic equation to find my final velocity, then initial and final velocity should be the same. First thing on the list, I'm using my iPhone where I'm going to record my experiment. At the same time, I'm going to use it as a timer so I can keep track of time on the whole thing. Next up is the blue tape, where I'm going to use it to mark the spots where the projectile I launched lands. Since I already don't have enough projectiles to use for all my trials, that's why I'm using blue tape as an alternative to that to reference where it lands. Next is the slingshot, where I'm going to use it to launch my projectiles. Now onto the cork balls, where I'm going to use them as a projectile itself. Next up is paper, where I'm going to use it to record down the data I found it from the experiment. Up next is the measuring tape, where I'm going to use it to measure how far from the start my projectiles landed. Now onto the calculator, where I'm going to use it to do my calculations on my experiment. Now onto my mechanical pencil, where of course I'm going to use it to write down everything from my data to my explanations. Next up is my screwdriver, where I'm going to use it as a reference of my starting point, so every time I go measure my distance, I don't have to forget where I launched my projectile at. Next are my wood planks, where I'm going to use them to hold my phone in place while recording the experiment and time. Lastly is my protractor, where I'm going to use it to measure the angle of how much I'm aiming for my slingshot. As you can see from the picture, the slingshot with the cork ball already in place I'm holding is on the left side of the screen, where the screwdriver marks the starting point is. On the right of the screen, when the ball lands, is when I can go and mark it with blue tape, since I don't have 5 projectiles to launch for 5 trials. My phone itself, which is one of the materials, is being held by the 3 wood planks I mentioned earlier. Also, every time I launch, I'm going to measure how far I travel by using a measuring tape. Later on in the video is where I'm going to reference the part where I'm using my protractor, calculator, paper, and my mechanical pencil. The design of this experiment is to collect the distance and time for each trial. This is if you didn't see the screwdriver from earlier. As you can see for trial 1, my projectile traveled 140 centimeters in the time span of 1 second. As you can see for trial 2, my projectile traveled 164 centimeters in the time span of 1 second. As you can see for trial 3, my projectile traveled 169 centimeters in the time span of 1 second. As you can see for trial 4, my projectile traveled 166.5 centimeters in the time span of 1 second. As you can see for trial 5, my projectile traveled 166.5 centimeters in the time span of 1 second again. This is where the projectiles landed during the 5 trials I did. Since all my measurements were in centimeters, I changed it to meters, but also since I had multiple trials, I averaged it out to 1.612 meters. On paper, where of course I wrote it with a mechanical pencil, I recorded down my data to create a table in which you can see as time went by, the horizontal position also increased. Meanwhile, the vertical position went to its peak height down back to the ground just from the cork being launched upwards. As you can see from the graphs I did for vertical, the position time graph showed the position increasing and decreasing as the cork ball was heading upwards and downwards back to the ground. The velocity time graph showed a constant positive and negative velocity as the cork ball was heading upwards and downwards. Despite the velocity change, it was because the cork ball was about to head downwards. The acceleration time graph showed constant acceleration until 0.50 to 0.75 seconds, where the cork ball was already heading upwards, was then head downwards. As you can see from the graphs I did for horizontal, the position time graph showed the position constantly increasing as the cork ball was moving in the air as time went by. For the velocity time graph, you can see as time went by, the velocity of the cork ball in the air was constant all the way through. For the acceleration time graph, you can see the acceleration was constantly 0 as the velocity from the previous graph didn't change at all when it was constant. For the calculations, first I need to find the horizontal velocity by putting the total displacement of 1.612 meters per second into the calculator, divided by total time of 1 second, which I get 1.612 meters per second for my horizontal velocity. Next, I need to find the vertical velocity by tangent 4 by 45 degrees from measuring the angle earlier, multiplied by the horizontal velocity of 1.612 meters per second to get the vertical velocity of 1.612 meters per second, which then I calculate for the average initial velocity by using vertical velocity of 1.612 meters per second divided by sine 45 degrees to get the average initial velocity of 2.280 meters per second. Next, I need to calculate my final velocity, where I can use the already calculated initial velocity of 2.280 meters per second plus gravity of negative 9.8 meters per second squared times the time of 1 second to get the final velocity of negative 7.52 meters per second. The percentage of error I did was based on the calculated and experimental value of the angle used in this project. In conclusion, my findings didn't really fit my hypothesis, as my initial velocity of 2.280 meters per second isn't the same as my final velocity of negative 7.52 meters per second. What was learned was possible sources of error that I'm about to list can get in the way that can affect your data and calculations. Possible sources of error would have been air resistance, wind, and the slingshot itself. Percent error was 37.47% because of the wind, air resistance, slight adjustment of the slingshot that affected my experiment when I launched my projectiles. The wind pushed the speed of my projectile, making it look like the angle I launched was bigger than I had measured. Also, the air resistance had an impact as it was putting force in the other direction of the wind as the ball was in the air. Slight adjustment in the slingshot was mainly due to me adjusting myself in a comfortable position as I was outside for 2 hours exhausted. Experimental errors being I didn't get the vertical position when I was out there doing my experiment, but eventually there was a way to get it from calculating the formula while using the horizontal position. Also, at times when adjusting the slingshot can really affect the angle a little bit when launching my projectile. Reducing the errors, we can perform the experiment in a more controlled setting where wind and air is much less. We can also use multiple camera angles to record and the most precise data. In addition, instead of using a slingshot, more likely we should use a launcher that is more consistent on launching projectiles at the correct exact angle every time. Therefore, if these measures were put in place, then the errors would go down by a lot.